that error can be corrected, or burst errors. What is the meaning of burst error? Burst error essentially means you can see suddenly, let's say, if suppose you are transmitting some signal and there is a lightning in the, you can say, atmosphere, and because of the lightning, the message bit which are getting, transmitted, suddenly because of that, you can say all of the bits will be, obviously, you can say, will be in error. So, I mean, maybe thousands of bits may be in error, you can say burst errors. So those, how to recover the message in under those conditions also, that is the, you can say, concept of burst errors. And that means number of errors, you can say, which happen because of, such, you can say, some natural or some other, phenomena. So it's one of the most essentially applied block code in digital transmission and digital storage media also. Remember, I mean, digital storage media also, you can understand these particular codes importance there. So Hamming code, what is Hamming code? This was invented in 1948 by R.W. Hamming. His single error correcting code is an elegant one. Okay, so this is the first one, you can say, Hamming code. It should be easy to follow the encoding and decoding methods. Through the original code developed by Hamming was a specific 7x4 code. That means the total number of bits were 7 and the message bits were 4. Subsequently, all single error correcting linear block codes have come to be known as Hamming codes also. So this was a, you can say, single bit, and there are some theorems also. If you read in the Topselling book also, there is a topic on error control codes, where there are some rules, you can say, how many bits can be corrected, how many bits can be even identified by a particular code. So there are particular theorems which govern. So this code can cover or can specifically remove one bit. So this is the earliest code. And in any case, you know about parity. I think in your digital electronics, you read about parity checks. So parity checks is what? Essentially, you can say, if a parity changing after transmission from one, you can say, block to the other block, even in any, you can say, computer or memory to, you can say, your CPU, then obviously you can identify that because something wrong has gone. You can say parity flag gets lighted up, you can say. And so it's like, you can say, parity, that's also a particular code. In general, Hamming code is specified as 2m-1, 2m minus m-1. That is a block of k. 2m-1 bits are encoded together to produce a code word of length and is equal to 2m-1 bits. So m parity bits are added for every k information bits. Understand? M, that means 7 4 means 4 parity and k 4. Some example of Hamming codes are 7 4 15 11 31 26 63 57. All these codes are capable of determining two errors and correcting single error, as the Hamming distance of them is 3. So this distance is also important. That means the two codes, you can say, how many bits they are having in variation, you can say. So the distance is about, you can say, 3. Then you can detect two error and you can correct one error. By adding an overall parity bit, an NK Hamming code can be modified to yield n+1 k+1 code with. So a block code, essentially, such a code is known extended. I mean, you can do extending code also. We follow the polynomial approach to describe 7-4 Hamming code. The generator polynomial for 7-4 Hamming code is, I think that's another very good, perhaps for you to now pick it up, this particular topic, that polynomials are the basis of most of the, I told earlier on also, you can say, cyber security algorithms, cyber security codes. So it's a polynomials which form the basis of, you can say, generating those kind of, you can say, codes. So linear algebra, along with, you can see, these polynomials, that particular knowledge will help you if you want to, go for, you can say, some career in, you can say, data security, or you can say, of course, along with software that you will have to learn in any case. But as far as the, you can say, basis of, you can say, any, coding, that is, you can say, other, I mean, linear, you can say, algebra, and then you have these polynomials. So generator polynomial. Generator means, I think, a little bit of polynomial, as I said in the class also, like, Bessel, you can say, polynomial, then Legendre polynomial. Likewise, there are many polynomials. So the generator polynomial, you can call, I mean, which can generate, you can say, the corresponding polynomial is generator. Generator means which is capable of generating that particular, the kind of response that you want. So that x cube plus x plus 1, and the coefficient of xi minus r are elements of, I mean, generating function 2. The coefficients are 0, 1. However, all the polynomials are defined over an extended field of, you can say, this generating. The extension field of 7-4 Hamming code is GF2 to the power 3. In general, the extension field over which the generated polynomial is defined for 2m-1, 2m-1 Hamming code is, as you can say, generating function 2 to the power m. So the finite field of polynomial is defined in terms of finite set of polynomials as its element, okay, and a clearly defined set of rules for algebraic operation. For a convenience, the algebraic operations are often named as addition, subtraction, multiplication, inverse. It's also mandatory that there will be one identity element for addition, which is termed as 0, and one identity element for multiplication, which is termed as 1 in the set of polynomials. So the 0, 1 are viewed as polynomials in X, which is indeterminate. The field is said to be finite. Okay, so the field, as I said, linear algebra, you have to read a little bit about the fields also. A field is said to be finite as the result of any allowed algebraic operations. 1, 2, or more elements will be polynomial belonging to the same finite set of polynomials. Okay. Interestingly, if you can identify a polynomial in X, say Px defined over this particular generating function, such that Px is a prime and irreducible polynomial with degree m, then we can define a finite field with 2 to the power m polynomial elements. Degree of a polynomial is the highest, you can say, exponent of x in the polynomial. For the 7-4 Hamming code, m is equal to 3, a desired prime. Irreducible px, gx, you can say x3, because I mean we are looking for 3, you can say, parity bits. So m we are taking as 3, x cubed plus x plus 1. Now this was one possible representation of gf, 2 to the power 3. All polynomials whose degree are less than m is equal to 3 are element of this particular, and it takes only a group of m bits to represent an element in a binary form. So like field element, I say 0, polynomial, you can, polynomials, I mean, corresponding to 0. The possible binary representation can be that, I mean, if you represent in terms of, you can say, parity bits, if it is 1, it's 0, 0, 1. If it is alpha, x, 0, 1, 0, alpha square, x square, that's 1, 0, 0. Alpha cube, x plus 1, so 0, 1, 1. Likewise, you can define, you can see these polynomials corresponding to this, I mean, binary representation. Okay. Now, note that x7 is equal to 1 and x we are taking as x, and so on. I mean, x8, if it comes, it will be equal to x. Now, let's, for any Hamming code, the degree of message polynomial that's less than 3, the degree of generated polynomial gx is equal to 3, that we have already seen. The degree of code word polynomial cx, this should be less than 6. As an example, let us consider a block of 4m messages. Suppose I have a message bit as 0, 1, 1, 1, where 0 is the last bit of the sequence. Okay, so the corresponding message polynomial is, I am looking for x square plus x plus 1. If you follow non-systematic code, the code word polynomial is, you can say, mx multiplied by gx, so x square plus x plus 1, x cube plus x plus 1. So if you multiply mx with gx, we get this, you can say, and that essentially means x5 plus x4 plus x, you can say, 3 xORed with x3, x square xORed with this thing, you can say, and then you can write in this particular form, x5 equal plus x4 plus 1. So for a message, you can say bit 0, 1, 1, you can say the kind of, you can say, code word polynomial I'll be generating all that. So in a binary form, we get a code, like how do you write it? I mean, which particular bit will be finite, which particular bit will may not be. So if it is 1 here, suppose, since there are no element, you can say x, x square and x cube. So all 3 bits are here. x4, x5 are finite here. And then x6 is not there. So you get it 0. Similarly, if the message polynomial is this one, verify that the code word will be what? You can say corresponding again 1. You can say 0. If x is equal to, you can say corresponding to 0. You can verify that x square plus x, probably, you know, this should be, I think, x and x square should be finite, or maybe from this side if it is considering that. So the message polynomial in the same order like we calculated here can be calculated in this also, corresponding to this message bit, and verified. If you consider the general form of message polynomial, m cube x cube plus m is m2x square, m1x plus m0, where mi is equal to this, the general form of the code word. I think this is a little bit of mathematics. Probably you can appreciate it only when you have at least some exposure to, you can say, these polynomials or perhaps linear algebra. But all the same, I think if you are willing to learn, I think that's a good, you can say, starting. So Cx I can polynomial I can start up, you can say, corresponding. Now if we divide by this, by the generated polynomials, how do you divide, you can say, corresponding? I think you have learned all these things probably in your binary digital electronics paper. X5, X4, if you divide it by X3, I get what is what? X3. So I multiply it by X square, this becomes X5. This is my X3, and you get corresponding to X square. So X5 to X5, you can say XOR. If you do, that gives me, or they are cancelling. If you subtract 0, X4, this is 0, and then X square. Again, I go for X, and I get, you can say, X. So the remainder is corresponding to. Therefore, the code word in systematic form should be X5 plus X4 plus X cube plus X, a remainder. So that's my, you can say, corresponding to parity bits, and these are my message bits. Okay, 0, 1, 1 corresponding to, and 0, 1, 0. These are my parity bits. Now, similarly for the coder, you have a decoder also. Now, receiving a polynomial Rx is equal to Cx plus Ex, the decoder computes a syndrome polynomial. Now, how do you recover back? You might say that, sir, we are mixing message bit with the parity bits, but how do you receive back at the receiver end? Okay, so that's also important, because we have to separate out the message bits from the parity bits. So again, what we call in block codes is the syndrome polynomial. We generate that, and if the remainder is 0, the decoder declares the received word as correct one. That means there should be no remainder. If X is a non-zero polynomial, the decoder assumes that there is a single error in one of the 7 bits. In fact, the precise location of the erroneous bit is uniquely related to the syndrome polynomial. Note that the degree of syndrome polynomial is 2 or less. So the number of non-zero syndrome polynomial, you can say, because we are presuming that, our code cannot, you can say, identify more than 2 errors and correct 1 error as far as 7-4 Hamming code is concerned. So each polynomial form indicates a single error as a bit position. Then we can calculate which particular bit must have gone wrong. Once the location of the erroneous bit is found from the syndrome polynomial, the bit is simply inverted to obtain the correct transmitted code word. So that's what you can say corresponding to the code. Now, if we come to Reed-Solomon code, which is perhaps more widely used. Now, this forms an important subclass of the family of Bose-Chaudhary, Hockland-Game BCH code in popular form, which is called, and are very powerful linear non-binary block codes. So you have, this Reed-Solomon code. This is important subclass of this BCH codes. And this is capable of correcting multiple random as well as burst errors. They have an important feature that the generator polynomial and code symbols are derived from the same finite field. Okay, generator polynomial and the code symbols, they are derived from the same finite field. This enables to reduce the complexity and also number of computation involved in their implementation. So what is the, you can say, corresponding to Reed-Solomon codes are available with different code rates, with their code parameters are, you can say, code name is 31 to 27, block length is 31, number of information 27, error correcting 2, and then the code rate you can define corresponding to. Similarly for 31, you can say different parity bits you can add up. Okay, so here you can say adding up, you can say more parity bits, so I get more error correction power. Okay, so like other forward error control codes means, when you are transmitting, you call it, you can say, forward. The decoding of the Reed-Solomon code is more complex than their encoding process. Decoding becomes a little bit. Now you might say that why decoding is, even a subject of concern. Decoding, if it's taking more time, obviously your message recovery is slow. If message recovery is slow, your response of the, you can say, transmission or your the data recovery is obviously very slow. So that's not a very, you can say, good feature where you are looking for, you can say, megabits of, you can say, downloads, or maybe gigabits of downloads right now. So an iterative algorithm due to ER, this extension search algorithm for Reed-Solomon, you can say, and that's, you can say, maybe we let us avoid this particular you can say, little bit of more extensive discussion. Just to give an example that how that can be, these particular codes are useful for transmission. Now, if the allowable bandwidth expansion for error control codes alone be about 50% and let the hardware complexity permits us to consider block length of 31. Now, remember that because more bits if you are adding, you will have to transmit more information. More information means more bandwidth. And bandwidth is an issue, perhaps you understand, it's very, very a costly affair. So in such a situation, we can think of this particular with the following, parameters we decide upon, you can say this block codes also, how many bits we want to add up, and then perhaps we want to recover it back. So this is a block diagram of a digital communication. I think this will be give perhaps better probably for a startup. If you have a message source, you have the source encoder. You understand meaning of source encoder? Source encoder means essentially we try to reduce the information bits. Let's say if I'm representing it in 4 bits, I want to reduce it by, let's say, 4 to 3. And of course, my message content should not be, you can say, anyway compromised. That's of course important parameter. So if I reduce 1 bit here, that's, you can call it compression sort of. Then obviously I'll be in an advantageous position further on. So this is serial to parallel converter, and then the Reed-Solomon encoder I feed is parallel to serial converter, and then additive channel quantizer, and this is my receiving. I have serial to parallel converter, Reed-Solomon decoder, you can say parallel to serial, and source decoder and message sync. That means these are the block forms that perhaps will work on a digital hardware. I think this is what you can say about adder for 2 elements and a Galois field, you can say corresponding to, this is how G0, G1, we can perhaps you can say how do we implement corresponding to our operation by adding up different, you can say, set of elements. I think this is a little bit. Now, if I can find, a little bit of, you can say, this particular more basic about, you can say, this Reed-Solomon or some other channel coding. Yeah, probably I think I should have started a little bit, you can say, from maybe this maybe probably more, you can say. But anyway, I think you got now a fairly good idea how the block code is, you can say. And this is where you can say, you might say that why coding is studied. This is studied, or this is important because this enables us to identify and correct errors, which is obviously important part of any communication system. So the primary function of an error control encoder-decoder pair, also known as codec, okay, is to enhance the reliability of message during the transmission of information carrying symbols through a communication channel. An error control code can also ease the design process of digital transmission in multiple ways, such as following. Okay, how? The transmission power requirement of a digital transmission scheme can be reduced by the use of an error control codec. This aspect is exploited in the design of most of the modern wireless digital communication systems, such as cellular mobile communication systems. Look here, even transmission power requirement also can be reduced. Even the size of a transmitting and receiving antenna can be reduced by the use of an error control codec, while maintaining the same level of end-to-end performance. For example, VSET. You understand VSET? What is VSET, students? जानते हैं VSET क्या होता है बच्चों?
No sir.
नो आई मीन आप देखते होंगे ना, जैसे इलेक्शन के टाइम पे हर डिस्ट्रिक्ट हेडक्वार्टर से आपको वहाँ उनके कॉरेस्पॉन्डेंट रहते हैं, ये वोट काउंटिंग हो रही है, इन आवर कंट्री all the districts, of course, right now we have far better, you can say, internet, connectivity, or you can say communication link. But earlier on, I mean, if you talk about, you can say, mid 90s, and even if in the early 2000 also, each district, even today also, each district has, you can say, link through VSAT, NICNet. This VSAT connectivity, you can say, connects the district headquarter with the, you can say, all other, you can say, districts across the country. So, I mean, this is a two-hop network. You can say you transmit from your one, you can say, station. It links up to a satellite, and then the satellite figures out which particular, region this particular, you can say, signal should go on. And so the switching center then transmits that or uplinks that particular message for the desired, you can say, downlink. Okay, so it's a two-hop network. And this VSAT, obviously you can say it's a satellite base. So obviously, if suppose there is some problem somewhere, some landslides are there, or some you can say other problems, discontinuity of you can say communication link is concerned, there this VSAT system can work, because it doesn't require you can say any kind of you can say connectivity. And that's why you can see these mobile vans of this particular so many channels, they make use of these particular services VSAT. You can say they uplink their you can say information, voice or other, and then they get it you can say connected to the desired destination. So that's a very I mean, maybe right now VSAT is not, because satellite bandwidths are very very costly you can say. So not many people want you can say a link up to, right now you can have a fiber link probably at a much cheaper rate. So and then whole country has fiber also, you can say more or less. I mean, private companies or government you can say based you can say companies, they have already had you can say network of optical fiber. And I don't know how many of you understand that optical fiber just started I think around 80s, 70s, up to 1970. Nobody believed that fiber can be used for communication. That must be an eye opener for to most of you as a student, that in 1970 the nobody believed that fiber can be used for communication links. The losses were so high, you can say maybe around 70 80 dB or 100 dB, more than that. So obviously, I mean, they cannot be used. And look at the technology now. People have, you can say, reduced that losses from 100 dB to, if you look at, mid 80s and the 90s, the losses are now about 1 or 2 dB, even less than 1 dB in some cases. So from 100 dB to, I mean, 1 dB now. So obviously this become a feasible solution. And then now you can say maybe in the last 20 years or 25 years, we had a lot of you can say fibers were laid down in anticipation that communication, obviously whether it's a telephony or it's a data, that's a backbone right now of our world you can say. Because without data and without communication, you can say probably we will be really in a very probably difficult state you can say. So that's how the, I mean, things have, probably you have a perspective of this particular development also. Access to more users to some radio frequency in a multi-access communication system can be ensured by the use of error control techniques like CDMA. Jamming margin in a spread spectrum communication can be effectively increased by using suitable error control technique. Increased jamming margin allows signal transmission to desired receiver in battlefield and elsewhere, even if the enemy tries to drown the signal by transmitting high power. So that means, I mean, you can use this particular, I mean, these codes are used even to make them more secure, or this to negotiate the, you can say, jamming signals. So, I mean, Shannon was the pioneering, you can say, in mathematical theory of for digital communication. I hope all of you at least know about it. I think Shannon was a great, you can say, he produced some great work and gave probably a foundation for communication, you can say. How? What I mean, and you'll be surprised to know he was a mathematician. And the subject of error control only coding, you can say, only came out of his, you can say, basic proposals, or you can say hypothesis, as a powerful and practical means of achieving efficient, reliable communication. What did he say? Okay, so the major categories of activities and error control coding can broadly be identified. In fact, he defined that, how much a channel can carry information. You must have heard channel capacity theorem. So how much a digital, you can say, channel can support, how much a wireless channel, suppose if you get a 10 megahertz of, channel, how much data you can transmit through that, provided, and that upper limit is defined by, you can say, channel capacity theorem. So the major, and then he says there exists a error control technique, which can make it possible. The major category of activities on error control coding can broadly be identified as the following: to find codes with good structural properties, good asymptotic error performance, to devise efficient coding and decoding strategies, to explore applicability of coding. I mean, that's what you can say the basics you can start with. And this is where you can say we can calculate this forward error control you are familiar with automatic repeat request, that is used in your networking. I hope you know about, because if you transmit some frame and that frame is not reaching properly, then the destination again makes a request in networking that you again automatic repeat request. So if it's not properly acknowledged, it has to retransmit this particular ARQ. So uh, now you have next class, next lecture, or I can continue. Hello, students. Hello. Should I stop? Hello, students. You want to ask some question? No, no student is responding or asking. Anyway, I'll be sending you tutorial, and that tutorial you can attempt. I think I hope at least you can solve that, and if not, please give me. Or I think you can submit those that submissions also to me. I mean, this particular tutorial sheet, I'll be sending it today probably. Okay.